This is part 9 of a series of videos about parametric curves and parametric equations. I'm aiming these videos at students who are in pre-calculus through multivariable calculus, but these are definitely useful for physics students as well because I've been using parametric equations and curves to model motion. The last video, part 8, was the first one where we used parametric curves to model straight line motion at a non-constant speed. Before I'd always done constant speed motion. In this video, I'm going to introduce you to two new commands in Mathematica called grid and plot to display graphs side by side and particular kinds of graphs. Really, grid is the main thing to help you display things side by side and also above and below each other. Plot is actually a more basic plotting command than parametric plot. It's going to plot regular functions, and then we're going to make use of that to help us understand the parametric curves. I'm also going to show you a couple programming techniques to help you reduce mistakes and find mistakes in your code. So, here's our example. From the last video, we are using parametric equations to model straight line motion of a person traveling between 2 points in 1 second at a non-constant speed. We're actually not specifying the particular kind of motion, we're just experimenting with different kinds of motions that still satisfy this. We can also quickly answer these two questions: how far did the person travel and what was the person's average speed? They were the same as the answers for the constant speed case. The distance here between these 2 points was 5 meters. That was the distance traveled still in the second example. And the speed in the constant speed case is just distance divided by time. In the non-constant speed case, it's the same. It's still 5 meters per second, but now you interpret that as an average speed instead of a constant speed. Here was our code from the last video that allowed us to illustrate an example going between these 2 points in 1 second. B is the time here in seconds, so to speak. That is not at a constant speed. You can see this is starting pretty slow and speeding up. The reason it starts slow and speeds up is because I'm using a function, t squared, that's not t. It is still increasing from 0 to 1 as t increases from 0 to 1. But because it's not t, that's going to make the speed not be constant. Why does it increase in speed? We'll see if we can figure that out in this video. The next thing I want to show you is a little programming technique that can allow you to save a tiny bit of time here if you're using this code over and over again. I'm going to create a new function. I'm going to call it h of t. That is going to be this function that I plugged into C. There's a t squared here and a b squared there. I'm going to make it be t squared. Notice again with functions you put an underscore, that's essential. Colon equals, not essential, but I like to put it. I like to put a semicolon after this as well. Technically speaking, semicolons in Mathematica suppress outputs. So it's not actually necessary here, but I like to separate these lines with a semicolon. I'm going to replace the t squared here with an h of t. Replace the b squared here with an h of b. And now this is going to do the exact same thing. What's the benefit? The benefit is now when I want to make changes to this, for example, change it to a t cubed or t to the 10th power, I only need to make the change in one spot right there instead of both of these spots. So if you're going to use the same code over and over again with different examples, in this case for this function h of t, it's a good idea to do this. T to the 10th is even more extreme than t squared. It barely moves at first, but then all of a sudden it moves very fast. Why is that the case? We can also experiment actually with fractional powers, like 1/2 power here. You should recall that t to the 1/2 is the same as the square root of t. What's going to happen here? See if you can predict it. Think about it on your own. This one's going to start out fast and then slow down. So that's not at a constant speed either, but it's in the opposite direction as far as the way it's behaving. It's starting out fast and slowing down. Why? We want to get to that now with a command called grid. Here's the basic syntax of grid. To, for example, create a square of these 4 letters, A, B, C, and D. Look at that, there's a square. You don't see an actual square around it, but they are in a grid. A square, so to speak, with these 4 letters A, B, C, and D. Grid is giving you this output. If you wanted a rectangle, say that looked like this, even though the letters are not in order there, you could do it that way. This is going to be the first row of the output grid. This is going to be the second row of the output grid. That's the basic syntax of grid. And we're going to use it here in a minute before I show you something else. But I'm going to show you something else first is what I mean to say. What I'm going to do next, before I show you how I'm going to use grid, is I'm going to copy and paste this entire code inside the manipulate into as the defining feature of a new function that I am creating by myself that I'm calling paraplot. Okay, that's not a built-in Mathematica function. I am creating it. I'm going to call it a function of b. Notice this is the syntax for functions. What am I going to use for the formula? Well, it's the entire code that I just copied. I just pasted it now. Does that make sense? I thought functions have to have numerical output or point output. No, they don't. They can have a graphical output in Mathematica. For example, now I can use this function and plug in a particular value of b. Think about what you think I should get. I get a graph. I got a graphical output. I got the graph frozen in time from this manipulate based on this particular h of t, frozen in time at b equals 0.5. If I let b go to 0.5 here, it should be basically the same graph. Actually, I can type in a 0.5 here. It's the same graph. These are the same graphs. Okay? I copied it twice there. Okay, so this is a function that takes numerical input and gives you graphical output. That's handy for isolating possible problems. If I can now embed this thing in manipulate and do the same animation as before with much less code, it's much less confusing. You are modularizing things, and that's a better way to go about programming things. Now we're going to make use of this with grid. Before I do that, I'm going to do a similar kind of example. I'm going to call it another new command that I'm calling xplot of b is going to be a regular plot. Notice I'm just using plot here instead of parametric plot of the function f of t with actually h of t plugged in for t. T will go from 0 to b. I'll choose a plot range here, different than the previous kinds of plot range I've used. Let's go to 0 to, well, let's go -1 to 2 for the horizontal direction, and might as well go -1 to 2 for the vertical direction as well. Alright, I think I'll make this blue. Alright, I think this looks good. This is going to be a function that also returns a plot. It's a regular plot. Look at that. That's a regular plot, in this case of f of h of t. What is that? Think about that. F is up here, -3t plus 2. Then I'm plugging h of t into that in place of the t. H of t was t squared, I believe. So I would really get -3t squared plus 2. No, h of t was actually square root of t. Let's change it back to the t squared. I might also want to have this on a separate line so I don't always get that same output. So h of t is going to be t squared. Look at this graph. This is the graph. Well, let me label things too. Do a little bit more here. Axes labeled tx would be the appropriate labeling. This is a graph of f of t squared over the interval from 0 to 0.5, over the interval from 0 to 1. It's going to look like this. Notice it's going between 2 and -1. It's decreasing from 2 down to -1 as t increases from 0 to 1. Just like the x-coordinate of your point here goes from 2 down to -1 as t increases from 0 to 1. This is telling you what the x-coordinate is doing. Let me do something similar for the y-coordinate. I'll copy and paste this. I'll change this x-plot to y-plot. Change the f to a g. Enter that. I can also do y-plot of 1. That's a function that's increasing from -1 to 2 as t increases from 0 to 1, just like the y-coordinate at this point increases from -1 up to 3, excuse me. We're off the screen, I think, here. Yeah, okay, let's change this here. Yeah, we're going from -1 up to 3 as t increases from 0 to 1. Let me put this all together now quickly in a grid like this. Now I'm going a little longer than normal here. Here's the basic syntax of what I'm going to do. Now I'm going to replace what goes in front of the first comma, paraplot of b. In front of the second comma, I think I'm going to use actually y plot of b here, and I'm going to use x plot of b there. Let's see if this works. It is working. We're seeing all three functions at once. I'm going to end this video now. I want you to think about the benefit of this, and in the next video we will talk about it more.